this lesson, we're going to solve rational inequalities. Rational inequalities. A rational inequality is an inequality that contains one or more rational expressions. Below, you will find examples of rational inequalities. Here are the procedures for solving rational inequalities. Step 1. Express the rational inequality in the form where 0 is on the right side and a single rational expression is on the left side. So, as in that example that you saw on the previous page, you saw some that had rational expressions on each side. If that's the case, you're still going to have to combine those rational expressions so that you have only one rational expression and it is on the left side and 0 is on the right side. After you do that, moving on to step 2, you're then going to set the numerator and also the denominator of those functions. Set them equal to 0 so that you can find the boundary points. Again, the boundary points are found by taking the numerator, setting it equal to 0 and solving for x, and then doing the same for the denominator, setting it equal to 0 and solve for x, and those values of x, those are your boundary points. Moving on to step 3, you're then going to make a number line using those boundary points. It is these boundary points that's going to divide the number line into these various intervals. You're going to proceed with step 4, which you're going to test a value within each interval and evaluate it for that number so that you can determine whether the output is greater than 0, and if that's the case, that region is going to be positive. If it is a value output that is less than 0, meaning a negative number, then you know that that region is going to be negative. You're going to, step 5, look at your original given inequality to determine what region you were looking for. Were you looking for positive values? Were you looking for negative values? And whatever regions or intervals satisfy the given equality, that is your solution. And you're going to not only graph your solution, but write your solution in interval notation form, just as you did with the previous section on polynomial inequalities. The only difference here is that you have a rational expression instead of a polynomial. So let's go ahead and get started in the process. So step 1, recall we want to get it in the form to where we have just the rational expression on the left side and 0 on the right. So we have a -2 there on the left side, and it's just a single whole number. So when we move it over to the other side, it's not good enough to just move it over there, because in moving it over there, you're going to have the inequality plus 2. You need to have just one inequality. So you need to turn it into an inequality itself. And to do that, you take the denominator of the inequality that you have, and you're going to multiply the top and the bottom of that by x plus 1. Because you know that for a whole number, to write it as a fraction, it's just simply written over 1, so 2 over 1. But I need to make sure that it has the same denominator as the given rational expression. So again, I have to multiply the top and the bottom, because with fractions, whatever you do to the bottom, you have to also do to the top. So now that I have it as a rational expression, I'm going to go ahead and move it over to the other side. And by the way, it really doesn't matter when you do that process. I could have subtracted 2 from each side and moved it on the left side, but as soon as I'm done moving it over there, I'm still going to have to write it with the same common denominator. I would still have to multiply the top and the bottom by that. So again, it doesn't matter at which point you do that. Now, because I'm moving it on the other side, I'm subtracting that. So now on the right side, I have 2 rational expressions with the same denominator, and that's great because that is the only time you can combine rational expressions. You can't add or subtract rational expressions unless the denominators are the same. And so now I have this first on the top. For the numerator, I have that first group of 3x plus 5, take away 2 times x plus 3. So you got to remember, because this group has a negative in front of it, that is going to change them to their opposite. Another way of looking at it is just to include that negative with that. So that would be -2 outside instead of just 2. So -2 times x is -2x. -2 times +1 is -2. So once we combine that, we got to next combine our like terms on top. So combine the x family, 3x minus 2x, and then combine the constant numbers, a +5 combined with a -2. Once we combine the numerator, that's going to leave us with our single expression of x plus 3 over x plus 1, and we have 0 on the right. And again, we got that x because 3x minus 2x equals x. 5 combined with a -2 equals +3. So we now have it in the form that we needed it in. That was step 1, to express it in the form where you have one single rational expression on the left side and 0 on the right. We have now completed step 1. Okay? Let's move on to step 2. Step 2, we're going to take the numerator and the denominator, set them equal to 0, and solve for x so that we'll know our boundary points. So we can do mental math and easily see that on top x equals -3 and on bottom x equals -1. So those are our boundary points. You just have to be careful that with rational expressions, if one of your solutions, in this case, is -1, if one of your solutions makes the bottom undefined, in other words, when you plug that negative in, you're going -1 in. When you plug -1 in place of x, you're going to wind up having a 0 on the bottom. And you know that anytime you have a 0 on the bottom of a rational expression, it is called undefined. So, just a little thing to remember when we get ready to write our solution, make sure you have a parentheses around this guy because your solution cannot include -1 because -1 would make this expression undefined. All right, so that was just a little thing to remember, but we don't have to worry about that until we get to the end anyway. Let's go ahead and look at what our number line would look like with these boundary points, because it's these boundary points that's going to divide our number line into these three intervals, and that's going to be from negative infinity to -3, and then from -3 to 1, and then the last interval there is from 1 to positive infinity. And you're going to do exactly the same thing you did with the polynomials of inequalities. You've got to test a value within that region. Looking at the original polynomial, we are looking for values that's less than or equal to 0, meaning we're looking for negative regions. So now let's move on to step 4, and where we can go and choose a point within that region and evaluate it into the given function. So moving on to step 4. In our first interval there from negative infinity to -3, I'm going to go ahead and choose to plug in -4. So into the given function, removing the x and replacing it with -4. In doing so, I can see that the top is going to give me a negative value, and so is the bottom. So a negative divided by a negative, I don't care what the output is. I just want to know whether it is a positive or a negative output. And in this one, because a negative divided by a negative makes a positive, everything within that region is a positive. So I already can see that that is one region I'm not going to be looking for, because I'm looking for regions that are less than or equal to 0. So it wouldn't be the positive region here. We're looking for negative regions. So let's go ahead and continue. Now we want to test that next interval, and we have a -2 here. So we can go ahead and plug in that. It's the only whole number within there, so it's easiest to plug in whole numbers. So let's go ahead and evaluate the function for -2. When we do that, the top is going to give us a positive number. The bottom is going to give us a negative. A positive divided by a negative is going to equal a negative. So everything within that region then has a negative, and that is definitely our region we're looking for. But let's continue on, because we don't want to just assume that the last region there is a positive, although I believe it is, but we want to check anyway. So let's go ahead and test 0 since it's within that region, because 0 will give us our output really quickly because it just zeroes things out. And as you can see, there's a positive number on top and a positive number on the bottom. A positive divided by a positive equals a positive. So just as we thought, yes, that region is a positive. Looking at our original polynomial, our original rational expression, we're looking for values that are less than or equal to 0. So that would be our negative region, and that would be the region in between. So our solution then, because we have a line underneath for this symbol, that means that you're going to include the boundary points. But which one did we say we could not use? Yes, if you remember, it was the -1, and the reason why, again, is because -1 would make the expression undefined. So we can put a bracket at -3, have that bracket there, but we cannot put a bracket at -1, because -1 cannot be a part of my solution. So to write this in interval notation form, it's going to look like so. And there you have it for this rational inequality. Okay, and this is how you would graph that. Again, open points, you could either use an open circle or parentheses. For closed points, you use a closed circle or a bracket. Remember, for this particular one, you had to use that parentheses at -1 because it could not be a part of a solution, because it would make the expression undefined. Let's do one more inequality. So here we have an inequality with a single inequality on the left side and 0 on the right. So we have it in the correct form. That's great. Now we can go ahead and proceed to step 2 to find the boundary points. We need to factor the top, set it equal to 0, and solve for x. Solve for x on the bottom so we can get our 3 boundary points there. So I'm going to go ahead and factor the top. Once I factor the top there, that's going to factor into x plus 3 times x minus 2. So we can see from the top, 2 of our boundary points is going to be -3 and 2. And then when we take the bottom, we're going to have that boundary point of -1. And again, in this case, -1 cannot be a part of the solution because it would make it undefined. So whenever we get to the end, if 1 is one of those interval values, we have to make sure that we do not put a bracket around -1, but instead make sure there's a parentheses around it if it is part of an interval. All right, so we have -3, 2, and 1. We're going to use those points to split up our intervals. And so our intervals is split up actually in 4 different regions. So from -infinity to -3, and then from -3 to -1, and then from -1 to 2, and then from 2 to positive infinity. So we're going to be testing 4 different values for this particular one. All right, so let's go ahead and move to the next step of choosing a point within each region and test it out so that we can locate our solution set. All right, so here we have the original given polynomial, and it is set to where it is less than or equal to 0. So what are we looking for here? Positive or negative? I want to see if you got it by now. So if you said negative, that is correct. So we're going to test these 4 regions, and we are looking for the regions where the sign is a negative. So let's start with our first region, and we're going to go ahead, that's from -infinity to -3. Let's choose -4 there and plug that in. So now we're going to evaluate the function. Everywhere we see a negative, we're going, everywhere we see an x, we're going to replace it with -4. Once we do that, let's see, on top there we have a negative. In the second parentheses, that will also equal a negative. A negative times a negative is a positive. So I'm going to have a positive number on top. Let's go to the bottom. I'm going to have a negative number on the bottom. A positive divided by a negative equals a negative. So the first region is negative. So we know that's going to be one part of our solutions in there. All right, let's go ahead and go to the second region, which is from -3 to -1, and the only whole number within there is -2. So let's go ahead and test -2, removing all the x's and replacing it with -2. So in the first parentheses, I'm going to have a positive. In the second parentheses, that equals a negative. A positive times a negative is a negative. So I have a negative value on top, a negative value on the bottom. A negative divided by a negative is a positive. So everything within that second region there is positive, so that's not going to be a part of the solution. So that's good because we don't have to worry yet about that being there. So next we're going to go to our third region, and look, we have 0 in that third region, so let's go ahead and plug in that 0 because we know it is always so easy to determine your solutions when things are zeroed out. So on top we have a positive times a negative, that equals a negative on top. On bottom you have a positive, so a negative divided by a positive is a negative. So the next region is a negative, and actually our solution is within that region, so I'm gonna realize that right here we're gonna have to put a parentheses there because remember, we cannot put a bracket there around -1. Now that last region should be a positive, but as I stated before, you should go ahead and just do the math and check because you never know when you might get that exception rule. So that region is from 2 all the way to positive infinity, and let's go ahead and test 3 as our test value. So finding f of 3. On top is a positive for the first parentheses, a positive for the second parentheses. So I have a positive on top and a positive on the bottom. A positive divided by a positive equals a positive. So just as we suspected, yes, that region is positive. That's not what we're looking for. We're looking for those regions that are negative. And also we have to remember that we cannot include 1 in our solution. So when we write it in interval notation form, we're going to have a parentheses around -1 and a bracket with where -3 is, a bracket where 2 is, and a parentheses around -infinity. So it's going to look like so once you write it in interval notation form. And there you have it, solving a rational inequality. Okay, and this is what your graph should look like once you graph it. Remember, it's either way. You can either use the circles or you could use the parentheses and brackets, whichever you prefer. And then on the bottom, as you can see, is how you would write it in interval notation form. And that's it for solving a rational inequality. Okay, that's it for this lesson. Thank you for watching MVP Tutorials by your instructor, Dr. Speights. I hope you'll join me in the next lesson. Please feel free to like, share, and subscribe. Goodbye for now.